In this video, I would like to go over the proof of chain rule so we can have a better understanding why chain rule is the way it is. First of all, we assume that we have a composite function, and this composite function is f of composite g of x equals to, of course, by definition, f of g of x. We have two layers of function here, and now we're going to introduce an intermediate variable. This intermediate variable is called u. We assume u is equals to g of x. Okay, so as a result, f composite g of x can be written as f of u, where u is equals to g of x. All right, so now we assume we call the composition capital F of x. And we are interested in the derivative of this capital F of x with respect to x. Now, I'd like to explain to you what do we mean by derivative with respect to x or with respect to y. Okay, by definition, derivative of f of x, assume it is differentiable, is defined as the limit. Okay, so I'm going to type the limit as h approaching 0. Okay, this is our familiar definition. And capital F of x plus h, subtracting capital F of x divided by h. Because the nature of capital F, which is a composition of f and g, okay, so here we're going to introduce some new notation. And these new notation, first of all, we're going to replace. Now we're introducing a new notation, which is replacing h, something we call delta x. Okay, it's read as delta x. So here's the notation. This is a commonly used notation that, we're going to use quite often, delta x. What does delta x mean? Delta x actually means change. Okay, change in x. For example, h, it has the same meaning as h. Same as h. But here we use the same row as h. But why we introduce delta x? Because we want to indicate h is a difference between x minus h minus x, right? So h is equal to the change in x, which is x plus h, subtracting x. So that's the change in x. So instead of, you understand why we introduce change of x, because very soon we're going to see change of in u or change in y. Okay, so now we have delta x, and delta x has the same meaning as h. So we're going to change h to delta x. So everywhere, let me start another line. Okay, let me start another line. So delta h is delta x replacing h. Okay, so when we see this definition, let me make it a bit larger. Okay, when we have this definition, we see that the derivative we are interested in is the capital F, x plus a change in x, in delta x, subtracting capital F of x. Okay? Now, in this definition, if we introduce a composition, right, we're gonna get F, right? Because the capital F of x is equal to F of G of x. Okay, so I'm gonna copy and paste this, so it follows us. We're gonna look, what is a capital F of x plus delta x? So now we're gonna replace x plus delta x, replacing x by x plus delta x. So this will be replaced by x plus delta x, and this will be replaced by x plus delta x, okay? For now, okay? So we're not gonna look at the u yet, okay, but we will. And next, okay, we're going to put this in here, okay? And now, of course, capital F of x, we know what that is, okay? And I'm going to remove this. We don't need this, right? So we try to keep it as simple as possible. And now we got F of G plus, okay, let me write another line right here. So F of G of delta x, and of course, oh, wait, sorry, my bad. Okay, I meant to copy this piece to replace F of x plus delta x. F of x, okay, capital F of x, of course, is just F of G of x. Okay, so we try, if this function is differentiable, this is how we find derivative by definition. Okay, so we're gonna put this away for the moment, and we're gonna put this above it. Okay, with our new notation, Now, we got a g of x plus delta x, subtract and get a g of x. So we're going to introduce another. Remember, we just introduced u, right? U is g of x. Okay, if there's a change in x, there will be also a change in u. So what will be delta u? Okay, so what will be delta u? Delta u, of course, is a change in u equals to g of x plus delta x. The intermediate variable also has change. So g of x. So this is called the delta u. Okay. Now, to simplify this, right? So by this time, this expression, now we can do further substitution. The further substitution is that g of x plus delta x, right? It is equal to, if we want to express this piece, and we can add g of x in this expression, in this identity equation, we can add g of x. So g of x plus delta x is going to equal to g of x plus delta u. Okay, let me find the delta u. Okay, so with that notation, of course, this is what? This is u, right? U is g of x. So g of x plus delta x is u plus delta u. So g of x plus delta x, which I just put it here, okay, is u plus delta u. Is u plus delta u. And of course, g of x is what? Is u. All right, so with this, let's take a look with the change in x and the change in u. Okay, when we try to find the derivative of a function, capital F, and we basically take f of, the numerator, which is also a change, right? So the top is actually delta y, okay? If we assume capital F is y, okay? Capital F is y. So this is going to be change in y, change in y, delta y. There, change in y, which is, the notation is shorthanded. The notation is shorthanded. In this shorthand notation, so let's take a look. Let's take a look, okay? After all of these introductions, we have a different perspective. And this different perspective is we're taking this limit, okay, which is equivalent to the original limit we're interested in, right? But this will be the change in y, change in y. So to find this limit, find the derivative with respect to x, the dx, we will need to find the limit of change in y divided by change in x. Okay? And next, with this shorthand notation, okay, of course, capital F is what? Is y, right? We introduced this. So now, this is dy dx. dy dx. Okay, so you have lots of new notations, okay? Now, we want to find this limit. So now we're going to put this away because we've already taken care of it and shorthand notation of it. Now, we are going to find the derivative. What we're going to do is that we're going to multiply by 1. Anything times 1 stays the same. And for this one, we're going to multiply delta u divided by delta u. We multiply by 1. After we multiply by 1, we're going to switch place with delta u and delta x. Okay, so this is a purely algebraic manipulation. So this is delta u and this is delta x. They switch the place. Now, what is delta u and what is delta x? Well, we just describe it. Now, let's look at the limit. Let's look at this limit. Let's look at this limit. This limit is delta y over delta u. Okay, hold on. This is delta x, by the way. Sorry, I have forgot to change the h here. Okay, which should be delta x. Forgive me. So this will be delta x. Delta x. Okay, we know delta x is the same as h. Okay, so delta x. If a function is differentiable, it is continuous. So when delta x is approaching 0, delta u is approaching 0. Okay, when delta x is approaching 0, delta u is approaching 0. So in this proof, right, what is delta y and delta u? So we're going to put them back in there. Okay, delta u is really, we can here change it to delta u approaches 0 because when delta u approaching 0, delta x approaching 0, delta u approaching 0 also. And delta y is this piece. And delta U is right there. This is delta U. So what is this? This is actually the derivative of f with respect to U. With respect to U. Okay, so that's the first part. So this piece has a limit. This individual limit exists. How about this piece? Delta U over delta X, right? So let's look at when we take limit of when delta X is approaching 0. And what is delta U? Delta U, we're going to bring it back where we had it. G of X plus delta X divided by delta X. And what is this? This is a derivative of G of X. So now, this piece individual limit exists, this piece individual limit exists. So the whole of it, we can apply limit law. We can apply limit law. So in this limit law, we can do the following. We can take limit respectively. We can take this limit separately from the other limit. We just take limit separately. And this result is f prime u, the derivative with respect to u, I hope you hear that, and the derivative of g with respect to x. So this ends the proof of the chain rule. So the conclusion is the derivative of this composition function, the derivative of this composite function, which is the derivative of capital F of X or the derivative of F composite G. Okay, however you describe it. Okay, is equal to the derivative of F with respect to U multiply the derivative of G with respect to X. And of course, in the end, you have to bring the U back where it is, right? U is G of X. So in application, so this is going to be G of X. You substitute U back. So that's finished. So this is the proof, and that's the chain rule. That's the chain rule. Okay, so example. Okay, I'm going to use some simple examples. For example, I'm going to have capital F of X equals to 2x plus 1 squared. This is the composition function, right? This is a composition function, and we are fairly familiar with it. So f of x equals to x squared, right? But this time, I'm not going to use x. I'm going to use u. F of u is u squared. It doesn't really matter because it's just a placeholder. And u is equal to 2x plus 1. Okay? So when we take a derivative with respect to u, this way, okay, or better yet, we write it in this manner, the derivative with respect to u squared right? U squared. And then multiply the derivative with respect to U dx, which is in here. Hold on, in here, I'll put it here, okay? The derivative du with respect to f of u multiply the derivative of g of x, lots of substitution, right? Lots of substitution, I will follow. But this is with respect to u, and this with respect to x. Du dx. Now the question is answered. Why we use delta x? Why we use du dx? Because when we use du dx, we indicate the derivative is with respect to whether it's with respect to x or with respect to the intermediate variable, which is u. Okay, so f of u is u squared, and u is 2x plus 1. So to find the derivative, okay, so let me, no, I should write this as a capital F of the derivative of f of x. This will be the right way to write it, okay? So be careful. This whole thing is differentiated. I'm going to show you the difference with respect to what, okay? So capital F of x, we take a derivative of the intermediate variable, which is u squared, okay? F of u. So that's u squared, because this piece is u squared with u equals to 2x plus 1. We're taking derivative of u squared with respect to u. So in that case, we get 2 times u. So this way, you can see it's more concise. And du dx, we take a derivative of 2x plus 1, and that equals to 2. Okay, so du dx, we know how to find it, right? That's pretty straightforward. The final answer is going to be 4 times u. But we want to express the final answer not using the intermediate variables. So we use 4 times u. U is 2x plus 1. There. Okay, so let's look at another example. So let's look at the other example, the second example. This one is also the one that we are familiar with, right? So we're not going to use any variables here. So we just see it as, okay, we just see it as we're taking derivative of the whole thing with respect to x. So derivative of something with respect to x. So now we're taking that with respect to, first we take it with respect to u, because we assume this piece is u. Okay, and what is u? U is whatever inside the parentheses. So to get that, we take a u raised to the power of 9 with respect to, we divide it by du, multiply by du, and then divide by dx. So you see the glimpse of our proof. You see the glimpse of our proof. Okay, divided by du, multiply by du. Okay, look at the proof we have. Divided by delta x, divided by delta u, right? Divided by delta u, multiply by delta u, right? So we have this setting in our proof right here. So we basically use that our proof in the simplified version, we get the derivative of u to the power 9, which is 9, u to the power of 8. Okay, and then we're going to differentiate the u with respect to x. And that's going to give us 3 times x squared plus 2 and minus 0, of course. So in the end, right, we're going to bring u back. Okay, so u, the original expression of u, we're going to substitute it back to be the same variable. So that will be the final answer. Now the question is, how do you show your work? How to show work? If you understand the whole process, typically showing work, you can show the reader that you use u or you don't have to. For example, when I take a derivative of this piece, okay? When I take a derivative of this piece, and I'm taking derivative, so this is when these notation is helpful. And this is also why the derivative, the notation is preferred, because we're taking derivative with respect to x, not with respect to u. And u is just an intermediate variable. Okay, you can show it this way. Okay, you can show it the d. Okay, and this piece is going to be u squared right here. Okay, and then du dx, but du dx, you can write it this way. You can write that u, the second u, as 2x plus 1. There are many different ways to show your work. Okay, this is just some of those examples. But of course, you want it to be very clear, right? So in the end, so you're going to have this line, right? And it's a 4 times u, and so that's, and then you substitute u back to where, you know, it was in relationship to x. If you show this amount of work, that'll be fine. Or as you're getting better at this, you may not even introducing u. Okay, so when you show work, you could just show this. In your mind, there's a u, but you don't have to show it explicitly. You can just show 2 times. I know I have a u here, and that u is 2x plus 1, right? So it's 2 times u, and then I'm differentiating 2x plus 1, that's equals to 2. And you also get the same answer. So you didn't explicitly inviting u into the picture. But that is okay too, as you're getting better, because in your mind, there is a u. You just didn't express it properly. Can your reader read it? I assume so. If you show your work like this, yes, your reader can read it. Okay, so now let's look at example number 2. You can show the work this way with u explicitly expressed, or you can simply write in the following way. Okay, you can simply show it, okay, or show work. You can show your work. You can show your work this way, okay, or you can just bring this back, right? The original expression is raised to the power 9, right? So you can just show it this way, okay? In your mind, you have a u to the power 9. So that's going to be u to the power 9. You're going to have 9 multiply u to the power of, you're differentiating the u to the power 9 minus 1, which is 8. And then you're going to differentiate the inside the parentheses which is 3x squared plus 2. Then you're done. So this much work would be sufficient. This much work would be sufficient. Okay. I hope this helps. Thank you for watching.